Welcome to Destiny. Today, we're diving into a cosmic mystery. What would it look like to fall into a black hole? A black hole is a region in space, like a bubble of warped space-time, with gravity so intense it pulls in everything around it. Imagine it tugging at the very fabric of the universe, not unlike a star or planet, but far more extreme. This bubble has a boundary called the event horizon, which splits the universe into two zones, the outside and the inside. Beyond the event horizon, the universe's fabric is stretched so rapidly that nothing, not even light, can escape its grasp. Our universe is home to countless black holes, but they're far enough away to pose no threat. Still, let's satisfy our curiosity and explore what we'd witness if we ventured too close to one. This thought experiment will deepen our understanding of these extreme cosmic phenomena and clear up some common myths. At the heart of our galaxy, the Milky Way, lies a supermassive black hole named Sagittarius A star. Picture this. We're in a spaceship, approaching it from a safe distance. Then, we leap into the void, beginning our descent. This journey will take roughly an hour and, sadly, will be our last. The spaceship stays behind, orbiting the black hole and observing our fall. Before we even begin our descent, we encounter a challenge. This supermassive black hole has gravity equivalent to millions of suns. Its pull is so strong that it gathers nearby stars and material into a dense, swirling disk of plasma around it. This disk spins at mind-boggling speeds, nearly matching the speed of light. As it churns, friction generates turbulence, heating the plasma to billions of degrees. This produces a torrent of radiation, visible light, ultraviolet, X-rays, and gamma rays that could blind or incinerate us instantly. For this journey, let's assume we're wearing an advanced spacesuit built to withstand extreme heat and block harmful radiation. Even so, the disk's brilliance is overwhelming, making it hard to see details or the stars beyond. So, we imagine our helmet has a special visor that dims the disk's glare, allowing us to observe it clearly while still seeing the starry backdrop. At first glance, the disk appears strikingly blue. Our visor filters out all but visible light, and within this spectrum, the disk emits more blue light because it's the most energetic color. It's similar to why very hot stars glow blue. Curiously, one side of the disk looks brighter than the other. Why? The material in the disk orbits at such high speeds that one side races toward us, while the other moves away. On the approaching side, light waves get compressed, arriving with higher frequency and intensity. On the receding side, the light stretches, appearing dimmer and less energetic. This is the Doppler effect, the same principle that makes a car's engine sound higher-pitched as it approaches and lower as it speeds away. Looking directly at the black hole, we notice the back of the disk appears distorted, curving around the event horizon to form a glowing ring. This happens because the black hole's immense gravity bends light, acting like a gravitational lens. Objects in seemingly one direction are actually located elsewhere, warped by the black hole's pull. The background stars also look slightly different, tinged blue. Though we don't feel it, the black hole warps time itself. Our clock ticks slower than those of distant stars, making their light appear accelerated and bluer than it truly is. Surprisingly, during the first 10 minutes of our fall, the black hole seems to shrink in our view, even as we hurtle closer. Why? It's a phenomenon called aberration, similar to what happens when you throw a ball through a moving car. To a passenger in a stationary car, the ball passes straight through at a 90-degree angle. But if the car is moving, the ball appears to come from an angle skewed toward the front. In our case, we're moving toward the black hole, and the light from the disk reaches us from a different angle, compressed toward the direction we're falling. This makes the black hole's image appear smaller at first. After those initial 10 minutes, we're zooming at 4% the speed of light. From here, the black hole starts to loom larger in our view. As we descend, our speed surges, and the light ahead grows brighter and more intense, while the light behind us dims. This is the Doppler effect again. We're catching up to the light in front, while the light behind struggles to reach us. If we glance back at the spaceship orbiting the black hole, we notice something peculiar. Its clock appears to tick slower than before. The effect is subtle but unmistakable. This is another manifestation of the Doppler effect. Imagine the clock sending out a signal every second. As we fall faster toward the black hole, those signals take longer to reach us, making the clock's ticking seem to slow down, almost like a movie in slow motion. Minutes pass, and we soar closer to the swirling disk of plasma surrounding the black hole. Suddenly, after 57 minutes of falling, the disk begins to fade from view. We've reached a critical point where the black hole's gravity is so intense that matter can no longer maintain a stable orbit. The plasma, caught in this overwhelming pull, spirals rapidly inward, and the pace of our descent accelerates dramatically. Just 2 minutes later, we're twice as close to the event horizon. We've entered a region called the photon sphere, where light itself can orbit the black hole. Here, any light from the outside world is destined to fall inward, just like us. From the perspective of the spaceship's crew, our image begins to fade and slow, freezing just at the edge of the event horizon. The light we emit struggles to escape the black hole's grip, taking longer and longer to reach the ship until it fades entirely. To them, we never appear to cross the horizon. But for us, the journey continues. Just 24 seconds after passing through the photon sphere, we reach the event horizon, the point of no return. Surprisingly, crossing this boundary feels unremarkable. There's no dramatic signpost marking the moment we slip inside the black hole. We can still see the light from distant stars falling alongside us. The spaceship, still orbiting, remains visible, its clock ticking ever slower. Even our own body, our feet, our hands, looks normal. Light, though trapped inside the black hole, can still travel upward relative to us, reaching our eyes. This reflects a key principle. While the black hole warps space-time on a grand scale, creating the horizon that isolates the interior from the outside, locally, space-time feels almost flat, and everything behaves as expected. Contrary to popular belief, the black hole's image doesn't engulf our view. Even inside, it occupies only about 15% of our field of vision, with the rest filled with stars. This is due to aberration again. As we plummet at incredible speeds, light from the sides and behind us appears squashed toward the front, contracting our field of view ahead and widening it behind. The spaceship, now far behind, seems to grow larger in our view, even as we race away from it. We've crossed the event horizon, and nothing extraordinary has happened. Yet. But any signal we try to send outward will never reach the outside world. Everything inside the horizon is doomed to fall inward, with no hope of escape. For now, though, all seems calm. That changes 30 seconds later, just before we reach the black hole's center. In an instant, we feel an overwhelming force stretching our body. This is spaghettification. The gravity pulling on our head, farther from the center, is vastly weaker than the force yanking our feet. The difference tears our body apart in moments. In our final fleeting seconds, it feels as though we're crashing onto a flat, pitch-black surface like the ground of a dark planet. Around us, a ring of light intensifies, growing brighter as we hurtle toward the center. A tenth of a second later, the remnants of our body reach the black hole's core. Our journey ends here, at least for now. Modern physics can't yet describe what happens at the heart of a black hole. Current theories point to a singularity, a point where spacetime's curvature becomes infinite, but many scientists believe these singularities may not truly exist. To fully understand these extreme regions, we need a theory that unifies gravity with quantum physics. Some hypotheses even question whether we could survive crossing the event horizon at all. In reality, black holes with angular momentum introduce complex effects, like multiple horizons and mathematical instabilities, which we don't yet fully grasp. Still, our current understanding corrects some common misconceptions. For instance, the disk around a black hole isn't orange, as some images suggest, but blue, due to its high-energy light. Those orange hues are often false colors used to show luminosity, not the true visible spectrum. Another myth is that we'd see the universe's entire history flash before our eyes as the black hole engulfs our view. This is false, as it overlooks the Doppler effect and light aberration. Many mysteries remain, and we'll need more advanced theories to uncover what truly lies at the core of a black hole. For now, our cosmic adventure offers a glimpse into the strange and wondrous nature of these enigmatic objects.